Alright, next type of problems in the review. Given f of x equal square root of 4 minus x and g of x equals square root of x squared minus 1. So keep in mind, if I talk about the square root of x, 4 minus x, for f, the domain, I would take 4 minus x set it to be bigger than or equal to 0, or x is less than or equal to 4. So anytime I use f, its domain carries with it. And anytime I use g, if you recognize, g is half a circle. Actually, I'm sorry, g is, for g, I take x squared minus 1 set it to be bigger than or equal to 0. Well, if I glance at this, that's a parabola shifted down 1 unit. It's bigger than 0 from negative infinity to negative 1, union with 1 to infinity included. So that's one thing I need to keep in mind. So when I take f plus g operating on x, that is f of x plus g of x. F of x is the square root of 4 minus x. G of x is the square root of x squared minus 1. So by using f, automatically its domain carries with it. By using g, automatically its domain carries with it. Whenever you have multiple cases, you want to put those on a number line, and you want the overlap. You want the portion that satisfy all of these cases combined. So negative infinity to negative 1, union with negative infinity to negative 1, union with 1 to infinity. So the overlap seems to be those portions. You know what? I should have. Okay. A better way is to use the colors. Negative 4 included and to the left. Negative infinity all the way to negative 1. And 1 all the way to infinity. So what you're looking for here, you're looking for the overlap, which is the green. So that would be a solution set. That would be negative infinity to negative 1 included, union with 1 to 4 included. And that would be the domain. Now when we say find f minus g of x, well, the good news, the work, f is the square root of 4 minus x, and g is the square root of x squared minus 1. You're done. But when we say find the domain turns out to be the same for those three. And for the last one, it's the same except g cannot equal 0. So the domain, automatically I copy it down, say domain, well, that's negative infinity to negative 1, union with 1 to 4. So I only need to find the domain once for f plus g, f minus g, f times g. F divided by g, I have to modify just a bit. F times g again, that is the square root of 4 minus x times the square root of x squared minus 1. You could leave it like that. You could write that as a single radical if you wish. You could leave it like that. You could FOIL, whatever makes you happy. And the domain, again, is identical to this. And if I take f divided by g, the square root of 4 minus x over the square root of x squared minus 1, domain is almost the same. I would say negative infinity to negative 1, but I notice the negative 1 comes from the green. Since this no longer can equal 0, I would exclude those. Union with, and the 1 comes from G as well, and 4 I will still include. If I was to look at the following functions, fg, well, f composite g, that is f of g of x, that is f g of x is actually the cosine of 3x. And that would be wherever you see an x, replace it by cosine of 3x over cosine of 3x plus 1. So now when we look for the domain, I'm going to have to get rid of one of those. When we look for the domain, we say, well, let's see, it's a fraction. We want the cosine of 3x plus 1 not equal to 0. We want the cosine of 3x not to equal negative 1. Where does that happen? Cosine equal negative 1 when we get pi plus 2 pi k. The angle equal that. So x cannot equal pi over 3 plus 2 pi over 3k. So the domain will be all real numbers except those values. So you could just make it official and say domain x such that x cannot be pi over 3 plus 2 pi k. And there it is. Next problem up, I would like to find G composite f of x and state its domain. Now I'd like to look at G composite f of x. That's G of f of x. That is G. F is actually x over x plus 1. Once I use that, I should know x cannot be a negative 1. Now go to G, there's G. Wherever you see an x, I see an x right there, throw all of that in. That's going to be the cosine of 3 times x over x plus 1. And we say, what's the domain? Well, it's right there actually. There's no other restriction. Domain, choose any x such that x does not equal to negative 1. If you'd like to use interval notation, you can. Looking at the next problem, f composite f. F is x over x plus 1, so automatically x cannot be a negative 1. Keep that in mind. Now go back to f one more time. Wherever you see an x, replace it by x over x plus 1. And this is a complex fraction. This is roughly a fourth of the problems that we see in this class, so you should really get that out of the way. LCD is x plus 1. This already has it, this already has it. If all the fractions at the top and the bottom had the same denominator, you ignore it and read the tops. That would lead to the top x over x plus 1. So that would be x over 2x plus 1. And of course, here x cannot equal negative 1/2. Add to that, or negative 1, domain x such that, that'll do the trick. Now I would like to look at the next problems. How about G composite G? So this is, in programming, this is called overloading an operator. That's when you have a function call itself, like, an alarm system. You get it to run all the sensors, then afterwards you run it again and again. So this is g of x. That's g. G of x is the cosine of 3x. Well, this says go to the cosine of 3x and substitute the cosine of 3x in there. So that's going to be the cosine of 3 of the cosine of 3x. I know it doesn't look pretty, but that's what it is. Domain, there's no restriction on the domain here because the argument could be anything. And then we get to the next, and that's h composite k. That's a tricky one. Be careful with that. There's h, there's k. That is h of k of x. That is h. K of x is radical x, so automatically x must be bigger than or equal to 0. And if I go to h, h is x squared. So take the squared and put it in there. And then my answer is x. Students see an x and think, oh, domain is all real numbers. If you use the radical, its domain must stick with it. So domain would be negative, no, would be 0 to infinity. And if I look at part, okay, what just happened? There we go. And if you look at the last part, L composite. So this is, you start with the right, that's L of h of g of x. You work from the inside out. The g of x, g was radical x. Nope, I'm sorry. G was cosine of x. Cosine of 3x. So no restriction there. H, so I'm going to take this and I'm going to square it. Still no restriction there. And L, that's going to be the absolute value of the cosine squared of 3x plus 2. And domain, there's no restriction whatsoever. There it is. Now, I really focused on that because we want to work backwards. What we need to apply what's called the chain rule. And for the chain rule to be able, for you to be able to use it effectively, you need to be able to reverse the order. Can you tell me two functions so that when you take the composition, you get that as an answer? So express the function in the form of f composite g. And this is how it works. You choose, there are many options. The one option you're not allowed to have, you cannot let one of these functions be x or the whole thing. Anything else will work. So for starters, you always start by picking g. If I let g equal, it'll be wise to let g equal the inside of the power function, the argument, which is the angle of a trig function, the power of a function, the argument of a log. So here, if I let g equal the inside of the square, h or f must be, so keep in mind, if I take this out, what do I replace in x plus 3 to get x plus 3 squared? I replace it by whatever you choose g to be, put an x instead. And that will work. There are other options. Here, if I let g equal, again, the inside, the 3x, now, f must be the cosine. Remember, you're going to have to substitute that in there, so that has to be an x. So these are two functions. If you take the composition in that specific order, f composite g, you will get the cosine of 3x. Again, here you have multiple options. One option to let g equal maybe all of this. And then f will be the square root of x. That will work. You could have let it be just x squared plus 1 if you want it. That's another option. And then f would be the square root of x over 3. Or you could have just let it be x squared. So there are many options. Any one of those will do. Let g equal, the important part is to choose the right sidemost function, because this is really f of g of x. You want to work from the inside out. If I let the inside be x plus 2, then automatically f would be the absolute value of x. You substitute that in there and it will match. And we're gonna have to do this 3 times. Well, no big deal. We're gonna take f of g of h. So choose h first. If I let h equal x cubed, that means g will be, remember, I'm gonna put an x right there, x plus 3. That means m equal, replace that by x squared. So again, from the inside out, if I let h equal the sine of x, automatically g will be, well, you're going to take this to replace that n. There must be an x. You're going to choose 3 plus x. Now, you must put all of that into m, and that will be the square root of x. So if you put that in there, you get the square root of 3 plus x, and if you put that in there, you will get the square root of 3 plus sine of x. And the last aspect of this section is dealing with a table, either tables or graphs. F of g of 2, these are a bunch of y values. So when you say g of 2, you're saying when x equal 2, what does y equal? When you say f of 2, you're saying when x equal 2, what does y equal? Always a y value. So, x equal 2 is right there. I want g. G is 5. And now what this is saying, if x equal 5, what is the f value? That's a 3. So it's kind of like a game. I think of it as a game, like, matching. Oops. Oh, I didn't realize. Right. I can't use it just like that. I could use it on those. Yeah. So you gotta be careful how to use this. Alright. If I go to part B, this is g of f of 2. When x equal 2, what does f equal? F is 1. When x equal 1, what does g equal? That will be f. There it is. When I get to the next problem, this is f of, when x equal 5, what does f equal? That's a 3. Now this says, when x equal 3, there's x equal 3, what does f equal? You're still at the same function. That's a 0. And if I go to this, g of, if x equals 0, what does g equal? That's a 1. And now, if x equal 1, Still, what does G equal? That's a 4. And if I am to go for f of G of 5, if x equal a 5, G would be a 6. And if x equal a 6, but there's no 6 up there, it only goes up to 5. So this is undefined. Or not defined, whatever you want to call it. And that's pretty much it for this section.